Hi there. In this video, we're going to start Chapter 3. So I'm going to do a Chapter 3 overview, and we're going to do 3.1 in this as well. So the overview is real small, and what I want to point out to you guys is that the entire focus of the course changes once we hit Chapter 3. So you've already seen the probability video, and that's not really indicative of the type of thing we're going to do either. Instead, what happens in Chapter 3 is that we take these big word problems that we've been doing, these big story problems, and we break them down even further. That's the main first step. So let me show you how this all fits together. So we're going to use the sample to learn about the population. And in Chapter 2, we saw how to collect data. In Chapter 1, we saw how to plan studies. Now we're going to start going the other way, right? And so that's called statistical inference, and that's what we're working on. And the focus of Chapters 3 and 4 is the two bullets at the bottom. If all we see are the data in the sample, what conclusions can we draw about the population? It's a really big question. It's hard to answer. The rest of this class is basically focused on that and how sure can we be about the accuracy of those conclusions. So first question, can we draw any conclusions? Second question, if we draw a conclusion, how sure are we that that is the correct conclusion to draw? Two very different questions, and it requires the whole rest of the course to answer them. So here's what we saw in Chapter 2. We saw all the combinations of variables. So there's 5 combinations. In the real world, there's 6, but we don't learn about the 6th one, okay? So if you have 1 variable or 2, we've learned 5 combinations of 1 or 2 variables, categorical or quantitative. And we've seen the quantity that's measured, right? Now, there's lots of symbols. Chapter 3 comes out pretty symbol heavy. You really just have to commit the symbols to memory once we get into the Chapter 3 material proper. This is still just an overview. And here's how Chapters 3 and 4 fit together with the stuff we've learned already. So we know that the goal of a statistical study is to learn about a population, to learn something about the population, right? The example we saw way early in Chapter 1, one of the first examples I did was about the study observing people washing their hands in public restrooms, right? So if all you have is a sample, how do you know what % of the population washes their hands? Like, how can we learn that? So we know that that's the goal. In Chapter 1, we saw how to plan a study and collect data from a sample. So if you're trying to learn about people washing their hands, you'd have to figure out the details of how to plan that study. Where do we send people? Do we have them comb their hair while they're in the bathroom to observe the other subjects? And then how do you collect the data? And how do you make sure the sample is representative? So you have to send people to different cities and things like that. In Chapter 2, we saw how to analyze data with summary statistics and graphs. So if you're collecting data on people washing hands and maybe you're comparing men and women, you'd use a segmented bar chart or something like that. We saw how to do all that. In Chapter 3, we actually go back a step and we look at more planning of a study, how to break down a study and really find out what exactly we're trying to learn about these populations. So that includes things like identifying the variables, and that includes things like explanatory and response. Then there's things called parameters that we're going to see here in a sec, all kinds of stuff. So we're actually doing here early in Chapter 3, and we keep doing this in Chapter 4 and beyond, but the focus is really here in Chapter 3 on further breaking down the problems. Then the last step that we do in Chapters 3 and 4 is statistical inference, where we actually learn something about the population. And so once we're done with Chapter 4, we'll have this wheel sort of completed, right? So the idea is we want to learn about, people washing their hands in restrooms. We need to identify the variables. We do explanatory response. Then these things called parameters. These are numbers that we're looking for in the population. Then you plan the physical details of the study. Where do you go? Who goes? How do they observe the subjects? How do you collect data? How do you get a representative sample? Make the graphs, and then later in chapter 3, and then in chapter 4, we learn exactly how much information a sample can give us about our population, and that would complete the goal of the study. So this chart is very helpful. Keep this thing around. If you're trying to figure out, like, what step am I in? Because the problem sort of is, we start off here and then we just jump over to here. And you have to remember that this stuff we've already studied is still going on. We just don't learn more about it. We've learned everything there is to know about studies in this class. We've learned everything we need to know about graphs in this class. So it's going to seem like it's kind of herky-jerky. Like, we start here and then all of a sudden we're over here and you're like, how does this connect? How does this variables and parameters connect to populations? But the idea is you have to remember that this is a process when researchers plan out these studies. And it's a long process. It takes us 4.5 months to do it. All right, so now we're going to jump right in and talk about the first section here called sampling distributions. Again, sampling distributions have parts of this and parts of this. Okay, it's an introductory section that leads us into more complicated stuff. All right, I'll let you read all that stuff. Here we go. Population parameters and sample statistics. So these are vocab terms. You have to commit them to memory. We are going to use the words parameter and statistic over and over every single day the rest of the semester. So a population parameter is a number that describes or summarizes some aspect of a population. And the way that this works is researchers, or you, if you're conducting your own study, you assume this is a fixed value, but it could be an unknown value. And again, to use the example I've been using, if you're trying to figure out what percentage of people wash their hands in a public restroom, that number exists, but we don't know what it is, right? So the number is some value that's just hidden from everybody. In the population. And then a sample statistic, this is the term we've been using, statistic, which is numbers computed from a sample. And sample statistics vary, but can always be computed. So statistics are never really unknown, sort of in the world, like the real world of statistics. You will always have some sort of sample or be asked to describe the process of taking a sample. And the value of the statistic will always be able to be computed from the data. Remember these two terms. You absolutely have to know them. We use this stuff over and over and over again. So here's the full chart. And this is the notation. So this is what we're going to be using when we describe parameters and statistics. So this is just a summary of everything we've studied, and it's updated to include some things that we hadn't really talked about up to this point. So this is the full table, everything 2.1 through 2.6, if we were talking about the population parameter or the sample statistic. So all of these should look familiar. You might not remember P1 minus P2, but we did talk about it. You might not remember mu1 minus mu2, but we did also talk about that. But just in case you forgot, here's everything on one slide. We talked about R and rho. We talked about B, which is the sample statistic for the slope of the regression line. It actually has a population parameter as well called beta. So the way this works, and you're going to see this more as we progress through chapter 3, researchers are interested in the population parameter. They collect a sample statistic. The sample statistic gives the researchers information about the parameter. This number is usually unknown. This number can always be computed, and this number gives us some amount of information, or gives researchers some amount of information. So again, keep this list handy. You're going to need it. So let's do an example. Let's just kick around some parameters and statistics and see if we can get a grasp of what's being asked of you early on in chapter 3. So state whether the quantity described is a parameter or a statistic and give the correct notation. So the way you have to do this is you have to decide population or sample first. That tells you parameter or statistic. Then you go back to the table and you think about what quantity is being described. If you forgot how to do those quantities, you have to go back even further to this table and you use the variables. So it's up to the individual student how far you have to break this down to get this answer. Do not guess. Do not assume anything. You have the tools to figure these problems out, even though they look different than you might be expecting. Just think about it and see how it goes. So let's do these. Hopefully, it gives you an idea of the kind of stuff we're going to be doing in Chapter 3. We're going to do other stuff too, but this is just how it opens. All right, the correlation between height and weight for all players on a 2014 Brazil World Cup team using data from all 23 players on the roster. So, population or sample. So we're told 23 players on a roster. That's a small amount. So it sounds like that would be a sample, but it's not. Because the quantity we're interested in is the correlation for all the players on the team. We have data for all the players on the team. So we have the population information. Now you might think, well, that's not much of a population. I thought populations were big. Try not to make generalizations like that in this class. If you're not sure, that's a good way to help guess what something might be. But here you're given all the information you need. We're looking for the correlation for all these players. We have the data for all the players. It's a population. Next up, height and weight are quantitative, right? So the quantity is the correlation. So what is the notation for the population correlation? Well, you can look back at the chart. Here's correlation. The population correlation is rho. And so that would be the answer. It's a parameter because it describes a population, and rho is the notation. Next up, proportion of registered voters in a county who voted in the last election using data from the county voting records. Here, you're not given a sample, so that's pretty much telling you it's a population. So this is going to be a parameter, and we want the proportion. So the parameter name that goes with a single proportion is P. So this is going to be parameter, and it's P. All the answers are on the next slide, but just telling you right now. We'll look at them as soon as we're done with Part C here. Part C, average number of television sets per household in North Carolina using data from a sample of 1,000 households. Here we're told it's a sample, and it says average. So if it's a sample and it's an average, that means it's a mean, and the notation for a sample mean is X bar, right? So it is a statistic. So this is early on, just the type of stuff you have to be able to do. Your online homework really doesn't have a lot of stuff like this. A little bit later it does, but on a test, this kind of stuff is perfectly inbound. So make sure you can do problems like this. So there's your answers, right? First one is parameter, which is rho. Second one is parameter, which is P. Last one is a statistic, which is X bar. And then I put a big note in here, and I really want you guys to take this to heart because we do jump around a lot in Chapter 3, and it's going to seem like the things aren't connected. But just keep this stuff in mind. Most of the rest of the class is concerned with using a sample statistic to learn about its corresponding population parameter. When researchers conduct studies to learn about a parameter in the real world, such as the difference in the proportion of people who become infected with the disease after receiving an experimental vaccine compared to those receiving a placebo, the actual value of the parameter is assumed to be unknown. So moving forward, pay close attention to the difference between identifying a parameter by name and identifying the value of the parameter. So what we saw here is two parameters identified by name, right? So let's go back and look. The correlation between the height and the weight for all players on the World Cup team is a parameter. It's rho. So its name is rho, or you could describe it using this, longer name. But we don't know the number. We don't know what the correlation is, but there's some correlation, right? If you mapped out or graphed out all the players, there'd be some dot plot, some scatter plot, and there'd be a correlation on that scatter plot. Same thing here, right? So if you are in some county and you want to know what proportion of registered voters actually voted, you'd have that information. That number exists. So P is the proportion, or you can write its longer name, but we don't know the value. So what you want to keep in mind is that as we progress, we're going to be computing values of things. The values of the sample statistics will become known values. They will be numbers. But you still have to identify parameters by name, even if you don't know the numerical value. So that might seem like I'm talking about the same thing, but I'm not. You can know the name of something without knowing the number that is represented by that name. So keep that in mind as you will see. And here's another note that you want to keep in mind moving forward. Solving most of the problems in the next two chapters does not involve much direct calculation. Essentially, the hardest direct calculation you have to do in the next two chapters, so we're talking about the next month and a half or 2 months of the class, is really just adding or multiplying a couple of numbers together for each problem. As part of the first steps, make sure you know how to find the following. So this is part of the breaking down process. Find the sample and find the population of interest. Make sure you can count how many variables are in a study and whether each is categorical or quantitative, which variables are explanatory and response, and the names and proper symbols. This is the main thing we do. We use technology, whether a calculator or StatKey, to do all of the heavy lifting for the numerical parts. But you, as a student, have to be able to do these the analysis parts where you're breaking everything down. Let's keep going. So sample statistics provide an educated guess for unknown population parameters. If we have a representative sample, the corresponding sample statistic is our best estimate or point estimate. Both of those mean the same thing for the true value of the unknown population parameter. So let me point out something else here too. This word estimate, some people read it as estimate, like the verb. This is a technical term. If you see this word, it means sample statistic. And a lot of students in the past have had trouble with this because you read it and you're like, oh, it's just an estimate. I don't need to worry about that. No. It's not just an estimate. It's the number we need to finish the problem or to do the problem. Make sure you're reading these vocab terms in the context that they're used. These are not throwaway terms. You need all of this stuff. So, talking about washing hands, in the section 1.2 PowerPoint, example 1, the sample proportion of p hat equals 85% is the best estimate for the parameter p, the proportion of people in the population who wash their hands after using a public restroom. So that this example at the bottom, and it's sort of just a callback to what we did before. So p hat is how we estimate p. Nobody knows the proportion of people who wash their hands in a public restroom. It is not knowable, but it can be estimated to a certain degree of precision with random sampling and some other stuff we're going to learn. So if you take a random sample, you get p hat equals whatever, in this case 85%. That's our best guess or best estimate or point estimate, they all mean the same thing, for the unknown population parameter. It's a starting value, an educated guess. So these are technical terms. Try to lock this in. If you need to just pause the video here and go back and review all the terminology so far, it's not a bad idea because we're just going to keep moving on and keep doing more and more stuff. So we expect that every sample from some population will have different characteristics and that statistics will vary between samples. This built-in variability from different samples causes uncertainty when estimating the population parameter. The parameter is a fixed value that is usually unknown, but it can be estimated to a certain degree of precision from a sample statistic. So, let's think about what all these things mean. When we talked about this sample of 6,336 people who were observed washing their hands, 85% of them washed their hands. If somebody else conducted the same study on a different sample, do we think exactly 85% of that other sample would wash their hands? Maybe, but probably not, right? Every group of people has different characteristics, right? The conditions of the observational study might be a little bit different locations, different observation techniques. So what happens is every sample gives us slightly different numbers. And that's where the uncertainty comes in, and that's why we have to understand probability to do statistics. Okay, so now we're going to switch the example up and talk about the NFL. Yes, I know this is not an NFL team, but it was the best picture I could find for a free license. So suppose we wish to learn about the mean annual salary of the population of NFL players by taking a sample from the population. So let's say you're interested in this and you want to know, I wonder what the average annual salary is for all NFL players, but you only want to directly observe a sample, not all the players. So how would you do that? That's what we're going to investigate here in this example, and we're basically going to use this example for the rest of the PowerPoint here. So what we can do is take a random sample of annual salaries and compute the sample mean X bar. This would give us a best estimate for the population mean. So even though for this particular example, we could just look it up because we have the data for this, but the idea is, what if we take a sample? How much information does the sample give us about the population? That's what we want to know. So here's a random sample of 100 NFL annual salaries, and you can see that StatKey tells us the sample mean is $2.404 million right here. There's your mean, and you can see the standard deviation, and you can see all this stuff. How close is X bar to the population mean? So before we go any further, just think about what the question is asking, because this is what all of Chapter 3 and 4 deal with, is stuff like this. So here we have a sample, right? There's so what year is this? 2015, I think? This is from the year 2015. It doesn't say it, but this is from the year 2015. There were 2,099 NFL players. Here we took a sample of 100 of them and got a sample mean. But this one sample doesn't really tell us a lot about the population mean. In other words, do we think the population mean is close to this number? We don't know. Do we think that this sample represents the population? Well, it is a random sample, as you can see. So this sample should have a lot of the same characteristics as the population. So we think that mu is going to be close to this number. But we know that every sample, if it's random, is a little bit different. So every sample we take is going to have a little bit of a different sample mean. So that's the tricky question we're trying to get at. So what we're going to do to take, in order to better understand the distribution of sample means, we can take more samples and look at the values of X bar from these samples. So here we have one sample. We know X bar. What if we took 1,000 samples? So here, this is a dot plot of 1,000 sample means. Every dot on here is an X bar, each from a random sample of size n equals 100 from the population of all NFL salaries. And this dot plot represents what we're going to define as a sampling distribution of the salaries of 1,000 random samples of n equals 100 NFL players. And these are all in millions, right? The units here are millions of dollars. So let's think about this. All of these dots are samples of size 100 from the population, and then the sample mean is plotted. So I know this is getting super duper abstract super fast. If you need more time to think about it, pause the video here and just re-watch everything up to this point dealing with these NFL salaries, starting at example 2. This is the fundamental concept of all of Chapter 3 and 4, is this sampling distribution. If you don't understand what these are, you're not going to understand anything else that we do in the class. We're done with pie charts and that kind of stuff. This is your future. Lots and lots of dot plots. So all of the dots in the sampling distribution are sample means from different samples of the same size from the population of all NFL player salaries. And we can see that one of the dots, one of the ones in this column here, is our original sample mean. So we took one sample and we looked at it and said $2.404 million. I think that's close to the population mean, but I have no way to tell. But if you plot 1,000 sample means, you see a distribution. And I know some of you are looking at this distribution and thinking, aha, I know a rule we can use for this type of distribution. And that's exactly what we're going to do. Okay, so the sampling distribution is the distribution of sample statistics computed for different samples of the same size from the same population. A sampling distribution shows us how the sample statistic varies from sample to sample. Values closer to the center of the distribution occur more commonly. Values farther away from the center occur more rarely. So this should be reminiscent of what we did in Chapter 2, the 95% rule. So what we're going to do is actually use the 95% rule to determine whether any particular dot in this distribution is unusual. Right? That's what we use the 95% rule for in Chapter 2, to find unusual values. Not outliers, unusual values. And if a value is unusual, it's going to tell us something. So let's see how this works. So the distribution of the sample statistics in example 2 is symmetric, bell-shaped, centered at the population parameter. So this is just a rule, okay? Sampling distributions have this quality, or these qualities. If samples are randomly selected, check, and the sample size is large enough, n equals 100 is actually pretty large, the corresponding sample statistics will have a symmetric bell-shaped distribution centered at the value of the parameter. This fact is one of the most important ideas in all statistics. Now, we don't know why it happens. We actually will never learn enough math in this class to know why this happens. But we are going to see that it happens. And after doing simulation after simulation after simulation, hopefully you are convinced that this is true and not some sort of mumbo jumbo. So the sampling distribution of a statistic is centered at the parameter, but what we really care about is the variability, the spread of the sampling distribution. So the standard error of a sample statistic, and we use the letters SE, is the standard deviation of the sample statistic. So go ahead, if you need to think about this, pause it, but I'm going to move around and show you some stuff. So we have a new name for a standard deviation if we're talking about, let's use this graph, right? If we're using one of these graphs. So the standard error appears up here in the corner. Now, we have this mean, but here's the thing. This mean is just telling us the center of this dot plot. So we don't use this mean for anything, okay? This is just, but we do use this standard error, okay? So because these dots are all random, this number moves around a lot. Just if you were to like do 1,000 samples and then do another one and then do another one, you'll see that mean kind of fluctuate, but this standard error usually doesn't fluctuate too much. And in this video and later videos, I'll show you how to do this stuff in StatKey. And so it'll make sense once you're able to do it on your own. For now, I'm just explaining the terms and concepts. So what we're going to do is use this standard error and build a 95% rule using that standard error. So that standard error is the standard deviation of the sample statistic. That graph we just saw had 1,000 sample statistics. How much variability is there? It's bell-shaped, it's symmetric. The standard error tells us how much variability. So of course, we use the 95% rule. And in the NFL salaries example, the sampling distribution is centered at the population mean mu. As of right now, we're assuming that mu is unknown, but we have that information, we can look it up. Because this sampling distribution was symmetric and bell-shaped, we can use the 95% rule to predict about 95% of the sample means will be within 2 standard errors of the parameter. So this should say means, that's a typo, that should say means. Will be within 2 standard errors of the parameter. So that means 95% of sample statistics will fall within the interval. Population parameter, that's our center, plus or minus 2 times the standard error. So that is just an updated version of the 95% rule that we used in chapter 2. So here I'm giving you mu. So I looked the value up and I said estimate the interval of values that are within 2 standard errors from mu. So what we do is we just type it in your calculator. So it's just, actually it's on the next slide. So it's just going to be 2.238 minus 2 times the standard error, and then 2.238 plus 2 times the standard error. Oh, I put it okay, it's 2 slides away. Let me go ahead and do this one then. So 2.238 minus 2 times the standard error, and then 2.238 plus 2 times the standard error. So go ahead and try this on your calculator, and you should get, here, I'll hold it up so you can see it. All right, 2.238 minus 2 times the standard error, 2.238 plus 2 times the standard error. If you need to pause the video, go ahead and pause it. Make sure you're getting these numbers. And I'm going to skip 2 slides ahead, right? There's the answers, right? Right? And again, make sure you're using proper units on all these. So about 95% of sample statistics should fall between our 95% rule. Now, what we're going to do is we're going to say, according to the sampling distribution, is a sample mean of X bar equals $1.5 million reasonably likely to occur, unusual but might occur, or extremely unlikely? So we need to have these numbers to do this problem. So let's keep these numbers, so write them down, keep them in front of you while we do this problem. So anything inside the 95% is really not unusual, right? That's like 95% of the stuff happens between these two numbers. But look, 1.5 million is way over here on the left side. It's not inside the 95% rule, so that is considered an unusual value. But look at our options: reasonably likely, unusual, or extremely unlikely. So the way that we do this is if it's comfortably inside the 95% rule, then it's reasonably likely. If it's near the edges of the 95% rule, it's unusual but might occur. If it's way out in the tails of the distribution, so if there's only a couple of dots out there or no dots out that far, then it's extremely unlikely. So this 1.5 million, it's way over here. In fact, there's only 1 dot in the entire distribution that's as unlikely as that sample statistic. So if there's only about a 1 in 1,000 chance of getting a sample statistic that's that unusual, then that's very unlikely, so extremely unlikely. Now, what about $2.1 million? Would a sample statistic of $2.1 million be unusual? Well, 2.1 is right about here. Well, that's comfortably inside the 95% rule. Again, 95% rule is those numbers there if you want to mark them down. So that would be reasonably likely to occur. Last one, $2.8 million. 2.8 is like right about here. Well, according to our 95% rule, 2.8 is right on the edge of the 95% rule. So that is unusual, but it still could occur. So anything close to the 95% rule boundary, or even a little bit to the outside, but not way on the outside, is unusual but might occur. Right? And you can see that just by looking at the 95% rule, right? So the lower limit is 1.642. This is extremely unlikely because it's way farther to the left. 2.1 is right in the middle of the interval, very comfortable, reasonably likely. 2.8, very close to that boundary, right? Here the boundary is 2.834. So 2.8 is awfully close to that edge. So it's unusual, but it still could occur. So this is not a hard and fast rule like we had in chapter 2, where if it's, just a little bit outside the 95% rule, it's unusual. This is a little bit more shades of gray. Closer to the middle, more likely to occur. Kind of in that 95% rule boundary, the edge, unusual, but it could occur. And then way out on the edge, extremely unlikely. If it's not on the graph at all, extremely unlikely. Okay, so let's do an example. This looks like one of your homework problems. So this is the population of NFL salaries that we saw. And it's all 2,099 NFL players in 2015, right? Of course, Aaron Rodgers is there, and he's very happy that he's making lots of money. So look at the population distribution. Way, way, way skewed to the right. There's a few outliers, right? Your Drew Breeses and Russell Wilsons and these guys skew the distribution way to the right. The vast majority of NFL players make around $500,000 a year. I'm not saying I'm crying for them that they're not making money. That's not what we're doing here. This is just data, and NFL season is in full swing. So I thought it was an appropriate example. So what we're going to do is use StatKey to generate a sampling distribution of sample means using a sample of size n equals 5 from these values. So I have the instructions here in the PowerPoint. I'm going to shrink the PowerPoint down, and I'm going to go into Reading View. So you guys, if you ever want to do this, Reading View is nice. If you ever want to watch a video or read a PowerPoint and follow along, go into Reading View, and then I'm going to go to the internet, and I'm going to go to StatKey, and I'm going to kind of do the PowerPoint and the StatKey at the same time to show you how I'm getting the answers that I'm getting. You have to do this for the homework. So this is a homework problem. That's probably too big. Let me shrink that down a little bit. Trying to get this thing to fit good here, because I can shrink down StatKey as well. All right, so StatKey. Oh, computer's running slow. Oh boy, I got way too small there. There we go. All right, so let me show you how to do this. Let me just get everything fit in here real nice. Oh, that should be fine. That should be fine. I think this is good enough. All right. Here we go. Should still be able to read everything. Here we go. All right, so we are example 4. Here we go. Okay. So part A, describe the shape of the population distribution. So we're gonna make a sampling distribution. You can see it's right here. Sampling distributions mean it's right here. It's where we're going to be going. And then we want to describe the shape of the population. Well, we already saw it. It's on a slide, but I want to show you where it is in StatKey, how to do this. Then we want to find the largest and smallest salary values in the population. That's part A, just talking about the population. So let's go ahead and do that. Again, if you look at here, I tell you how to do everything, but I'm just going to go ahead and click through it. So go to sampling distributions mean, and then the quantitative data sets you need for the homework are all built into the menu. There's going to be a problem later on where we're going to put some custom data in. You don't have to do it till I show you how to do it later on in chapter 3. So we're going to go NFL contracts, 2015 in millions, and then we're just going to click, and you're going to see, let me shrink it down a little bit more. Oh, that's weird. I don't know why it's doing that. There it goes. All right. You can see the population distribution here, right? So that's the one I showed you. So the parameter values are shown here. Remember, this is a population, so these are parameters, right? So N, remember, so N should be sample size. StatKey doesn't know that this isn't a sample, so it just uses N. There's your population mean, that's mu, and you're given a median and standard deviation. We don't need that stuff right now. And you can mouse over the individual values to see them. So just find the biggest number in the list. Obviously, it's Aaron Rodgers, 22 million. And then go down here, and then these are all in order. So if you want the smallest number in the list, just mouse over it. Okay, so for the homework, the population distribution clearly is skewed to the right. The smallest salary value is 0.405 million, and the largest is 22 million. So you just mouse over values to see what they are. All right, next up, so the next thing we have to do, thanks, Aaron, is we have to describe the shape of the sampling distribution. So look at what it says here. Use StatKey to generate a sampling distribution of sample means using a sample of size n equals 5. So what you do is you just click on here and change this to a 5. I know it's hard to see. Just click there, change it to a 5, and then the rest of the instructions are here in the PowerPoints. Okay, so then we're going to generate 1,000 samples. Okay, so one thing I want you to keep in mind is that when you start generating these samples, you get numerical values that pop up all over the place. You're going to get a mean and a standard error here. Those numbers are going to be different every time you do this because StatKey simulates a random process when creating these distributions. So if your answer is close to the correct answer, you get full credit. There's a tolerance on the homework. You don't have to get these exactly right. In fact, I prefer that you don't get them exactly right. What happens, though, is that if you're looking at an answer key or something, the answer key won't tell you the tolerance. You just have to know that being close is good enough on most of these. I know that's strange, but that's welcome to modern stats. That's how we do stuff. All right, so we already did this, right? So look here, the distribution is still skewed to the right. Not as skewed as the population, but it's still pretty skewed to the right. The smallest sample mean, so these numbers vary. So when on this turn, I can just mouse over these. So the sample, here, let me full screen this. The sample shows up here. So you can see, watch this number right here, it says mean. As I scroll through the dots, you'll see this number change, watch. And you just have to find the smallest number in the list. So this time through, the smallest number looks like 0.586. But the first time I did it for the PowerPoints, it was smaller. That's okay. The largest number in the list is 7.281. Again, looking at the PowerPoints, you can see that, yep, 7.1, so I got the same value, but the first time I did this, I got a much smaller minimum value. But notice the standard error is very close. So rounded to 1 decimal place, it's exactly the same. Follow the homework's instructions for rounding. I don't know exactly how many decimal places you need. I'm actually basing the answers here in the PowerPoints on the book version of this problem, not the homework version. Okay, so what did we learn here? Well, you can see that when you take samples of size 5 from this population and plot the sample means, the distribution is still skewed to the right. But you can see the standard error is smaller than the standard deviation of the population. So taking samples of a certain size reduces the amount of variability, right? There's less variability when we have a dot plot of a bunch of X bars, these are all X bars, compared to a bunch of data values, right? So this is the population data. This is where you sample from the population and plot X bars. All right, let's do the next part. Part B, where to go? Part B, we did that. Generate a new sampling distribution with samples of size 50. Describe the shape and the standard error. So we're going size 50, so click here, 50. And generate 1,000 samples. And you can see it looks way different, right? Looks very, very different. So the way I explained it, so I put the instructions in here, right? Choose samples of size n equals 50. Click 1,000 samples. When n equals 50, this is a symmetric bell-shaped distribution. It's not perfectly bell-shaped, but it's definitely symmetric and clumped in the middle. Remember, these graphs don't have to be perfectly bell-shaped to be considered bell-shaped. And so the center of the distribution is still the same, and the standard error here is, again, very different than what I got. So I got 0.85 million, here I got 0.4. But again, it's going to change, right? The standard error is definitely going to be smaller. So that is a random process. Those numbers fluctuate. As long as your numbers are even kind of close, you're going to be fine. So there you go. Let's do another one. I'm not going to show you the stat key. You can try it on your own. But the instructions for the stat key are shown in the PowerPoints. Feel free to try these on your own. You're going to have to do it for the homework anyway. I'm just going over the problem, how it works. All right, so using recent census data, it is known that 27.5% of U.S. adults are college graduates. Use StatKey to generate a sampling distribution for the sample proportion of college graduates using a sample size of 5. Describe the shape, center, and spread of the sampling distribution. Repeat part A using a sample of size 50. Repeat part A using a sample of size 200, and then comment on the differences in shape, center, and spread of the distributions. So what we're looking at here, this is a custom data set, and we're going to look at increasing the sample size as you sample. What does that do to the distribution? And I am going to do this one with you. I forgot that it was this problem. So we are going to work this one together, because this you have to be able to do for the homework. I know it's a long video, guys. Sorry. How long is it so far? Oh, not bad. Not bad. As long as it's shorter than the probability one, right? Okay, so the instructions are in here, how to do it. So click on Sampling Distributions, Proportion. There are data sets built into the left side. We're not going to use any of the custom data sets. Some of the homework has used, the built-in data. Some of the homework has used the built-in data. We're doing a custom data set here. To enter a custom proportion, click Edit Proportion. And we're going to type in the proportion given in the problem, right? So it says 27.5% of U.S. adults are college graduates. So we have to type in 0.275. Now, there is no population distribution because it's categorical data, right? You only have a population distribution with quantitative data. So think back to what we did in Chapter 2. We didn't start talking about distributions till Section 2.2, which started quantitative variables. So we're going to do samples of size 5. And then we're going to generate 1,000 samples. Boy, that's an ugly graph, isn't it? So you can see that this distribution is skewed to the right, right? We even have outliers out here, right? This guy's way out here. Here, I'll zoom it in a little bit. Here we go, it looks a little bit better. So you can see this is skewed to the right. I know it's an ugly graph, just get used to it. And so the mean, so just point this out one more time, because students goof this up all the time. This number that it shows for the mean is this triangle. That is not what we record for the center of the distribution. This is a sampling distribution, so it's centered at the original population number. For this particular example, it just happens to be the same. But I can do this again, and now it's a different number. So if I say, where is this distribution centered? You write down this number, not this one. Sometimes it just coincidentally is the same because it's random. The standard error is this number. Okay, so we do not use this number. We do use that number. I know it's tricky. Again, you just got to get used to it. Write it down somewhere. You're going to be doing this every day for the next month and a half. All right. So that's pretty close to what I got the first time I did the problem, as you can see. Oh, lost my internet there. There it is. There you go. So remember, the center is the population parameter, and the spread is given by the standard error. So it's not bell-shaped, so we can't use a 95% rule on this, right? So let's try part B now. Repeat part A using a sample size of n equals 50. All right, so we just change this to a 50. Generate 1,000 samples. Look at that, symmetric bell-shaped. Actually, it looks like a perfect pyramid. Who knew? And notice that the center is not this number. It's always the population parameter in section 3.1. The standard error, 0.063, that's the same thing I got the first time I did it. This is symmetric and bell-shaped, so we could use a 95% rule if we wanted to, which we will do, but just that's a little later. This video is almost done. Last one, we want to do samples of size 200. Go ahead and do 1,000. Still symmetric, still bell-shaped. Yeah, I know it's a little pokey and weird, but just it's going to be pokey and weird. But the general shape is symmetric and bell-shaped. Standard error 0.031, standard error 0.031. Center, population parameter 0.275. So make sure you can do all this. If you need to pause the video and go back and do all that again, this is word for word a homework problem pretty much. Make sure you can do it. We're going to be using StatKey a bunch starting really right now. And in part D, we have to give a summary of the exploration. So parts A, B, and C, what did we learn? When the samples were small, the distribution was skewed, but larger samples result in a symmetric bell-shaped distribution. Keep that in mind. We already covered that earlier in this section slides. It's in green. Go check it. Or maybe it's blue. I can't remember. It's blue or green. The center of a sampling distribution is always the population parameter. We're given that it's P equals 0.275, so you always write that down. And one thing we also noticed is that larger samples result in smaller standard errors, right? We can see right here. When the samples were size 50 each, the standard error was 0.063. When the samples were increased to size 200 each, the standard error got cut in half. So larger samples mean less variability among the sample statistics. That's a very important fact, and it's actually shown here. So this is just the same example we just did. This shows 50, 200, and 1,000. This is the image from the textbook. And as the sample size increases, the variability of sample statistics tends to decrease, and the sample statistics tend to be closer to the true value of the population parameter. So two things are going on at once. The standard error is shrinking as the population increases, and the shape of the distribution becomes more and more bell-shaped. So larger samples give us a more perfect bell shape and a smaller standard error. Both of those are useful for what we're going to be doing in future sections. And the last thing, I know it's a long video, guys, sorry. Random sampling will generally yield a sampling distribution centered around the population parameter. That's how it works. However, non-random samples may be biased, in which case the sampling distribution may be centered around the wrong value. Collecting the sample data in a way that biases the results can lead to false conclusions about the population. So this is what we talked about in Chapter 1. Well, this is one of the effects of sampling bias. If the sample is not randomly selected, or there's other, biasing factors, then the center of the distribution, it gets moved around and it's not centered at the parameter, which would lead to false conclusions. All right, well, that's it for section 3.1. Make sure you're checking out these concepts to remember, because this stuff comes back over and over again. Here's some extra practice, as per usual. There are video solutions for the book examples, and there's some extra book work you can do. A lot of those are homework problems. The answers to the odd ones are in the back. Well, that's it for today. So study hard, and let me know if you have any questions. Until next video, see you later.